So how could something appear if there's nothing to account for it? Let's start where our understanding is strongest, in classical physics. In classical mechanics, if you want a particle to move, you push it. If you want a field to exist, you set up charges or magnets. In that world, nothing would mean no particles, no fields, no radiation, no heat, just an empty void with no properties whatsoever. And in that classical picture, nothing happens. The mathematics is perfectly happy with an empty stage. If there's no actor and no script, the play simply doesn't begin. So if classical physics were the complete story, the question would be answered. Something cannot come from nothing, period. But the historical problem was that classical physics kept stumbling over actual experiments. It wasn't one spectacular failure. It was a whole series of small, persistent facts that refused to cooperate. Hot objects give off energy in ways classical theory couldn't explain. Atoms don't collapse, even though classical electrodynamics says accelerating charges should radiate away all their energy. Light knocks electrons out of metal only if the light has the right color, not just enough brightness. Each of these is like a small note from nature saying your idea of emptiness, motion, and energy is incomplete. Now you might say, fine, but those are complicated things like atoms, radiation, and materials. What does that have to do with nothing? Actually, quite a lot, because the solution wasn't to add a new kind of matter. The solution was to change the bookkeeping rules themselves. Here's a simple thought experiment. Imagine a tiny mass attached to a spring, an oscillator. Classical physics says if you remove all energy from it, it sits perfectly still at the balance point. Position fixed, momentum zero. That would be the quietest possible condition. Now we make it cold, colder, even colder, trying to remove every last bit of motion. If the world were classical, we could freeze it into perfect stillness. But quantum mechanics adds a requirement. You cannot assign an exact position and an exact momentum at the same time. It's not because your measuring instrument is crude. It's because the theory fundamentally doesn't allow a state with both perfectly defined. This isn't a slogan to memorize. It's a basic fact about how the wave description actually works. The more precisely you locate the position, the more the wave must be built from a range of different momenta. The more you insist on precise momentum, the more spread out the position becomes. The result is that our oscillator cannot have exactly zero energy. If it were exactly at the balance point with zero momentum, it would have perfectly definite position and momentum, which isn't allowed. So the lowest energy state, the ground state, still has a little wiggle, not because something else is shaking it, but because the state of absolutely nothing happening is forbidden by the rules. Already we've found a crack in the classical idea of nothing. The quietest state isn't perfectly quiet. It contains unavoidable fluctuations. And notice what we did. We didn't bring in fancy cosmology. We just took a simple spring and asked what zero energy would mean under quantum rules. Now take the next step. In modern physics, we learn to describe forces not mainly as pushes between particles, but as fields that fill space. Electric and magnetic fields aren't just convenient bookkeeping tools. They're physical. They carry energy. They can move as waves, which is what light is. That idea became clear with Maxwell. You can have electromagnetic waves traveling through space, even with no charges present where the wave is passing. So empty space in classical electrodynamics can still contain a field. If you set it up, it can exist on its own. But if you then apply quantum mechanics to fields, something remarkable happens. Each mode of the electromagnetic field, the part that wiggles at a particular frequency, behaves like an oscillator. And we just learned an oscillator cannot have zero energy. So when you apply quantum rules to the electromagnetic field, even in the absence of any photons, the field still has a minimum energy per mode. This is called zero-point energy. The name is almost playful. It's the energy of the zero state. At this point, a reasonable person objects. Wait, if empty space is full of zero-point energy, why don't we notice it? Why doesn't it heat things up? Why doesn't it tear atoms apart? Where is it? Good. That objection is exactly the right kind of discomfort. Physics moves forward when you push on an idea until it either breaks or becomes clearer. Here's one way it becomes clearer. Energy matters when differences matter. In many situations, a constant addition to energy is invisible. Only changes can produce forces or motion. If every state of your system has an extra constant added, no experiment inside that system can detect it. It's like shifting the 0 point of gravitational potential energy. You can choose where zero is, and only differences appear in motion. For a long time, physicists treated the vacuum energy of fields as such an offset, a formal number you subtract away because it doesn't seem to affect anything you measure. But then nature again wasn't perfectly cooperative. It turned out that in certain setups, changes in the vacuum energy are actually measurable. The most famous clean example is the Casimir effect. Take two uncharged metal plates extremely close together in a vacuum. Classically, there's no reason they should attract each other. No charges, no fields, nothing. Yet quantum electrodynamics says the allowed electromagnetic modes between the plates are restricted compared to those outside. If the vacuum has fluctuations in all modes, then restricting the modes changes the zero-point energy as a function of how far apart the plates are. A difference in energy as a function of distance is a force, and sure enough, an attraction is observed, so the vacuum isn't merely absence, it's a physical state with structure, and that structure can push on objects when you change the boundary conditions. Now at this point you might say, all right, space isn't empty, it's full of quantum fields in their ground state, but then it's no longer nothing, so you've just played a word game. You started with nothing, quietly replaced it with a complicated something, and then declared victory. That's a reasonable accusation, and it forces us to be more careful. When people say nothing, they usually mean no particles. They picture an empty box with no electrons, no atoms, no light. In quantum field theory, no particles doesn't mean no fields. Particles are excitations of fields, like waves on the surface of water. You can have a calm surface without waves, but the water is still there. So vacuum means no excitations, not no underlying entity. And the vacuum still has fluctuations because the fields cannot be pinned to exact values everywhere with exact rates of change. The vacuum is the lowest energy state consistent with the quantum rules, not a literal non-existence. So, if something from nothing means particles can appear where previously there were no particles, then the answer is yes, that can happen, but with important conditions. In quantum field theory, fields can exchange energy with one another and with external sources, and excitations can be created in pairs. The simplest reason pairs show up is bookkeeping. Again, conservation laws. For example, you cannot create a single electron out of the vacuum because you'd violate charge conservation. But you can create an electron and a positron together because total charge remains zero. If you supply enough energy, say with a sufficiently energetic photon near a nucleus to handle momentum conservation, the pair can become real detectable particles. In that case, nothing mysterious happened. Energy went in, particles came out. It's like converting one form of energy into another. But there's a more subtle phenomenon people often point to: virtual particles popping in and out of existence. This language is both useful and dangerous. It's useful as a picture for how interactions are calculated. It's dangerous if you think of virtual particles as little balls that literally appear in space and time, borrow energy, and then return it before anyone notices. The theory doesn't actually say that. What it says is that when you calculate the probability for a process, you sum over intermediate contributions that don't satisfy the usual energy-momentum relationship for real particles. These intermediate contributions affect measurable quantities like the Lamb shift in hydrogen or the magnetic moment of the electron, so they're not just fiction. But calling them particles popping out of nothing is a metaphor for a piece of mathematics. If you take the metaphor too literally, you'll end up confused. So, where are we? We've learned something important and slightly unsettling. The closest thing physics has to nothing, the vacuum, still has properties. It's a state of fields. It fluctuates. It can produce measurable forces when confined. And under the right conditions, it can be excited into real particles provided conservation laws are satisfied and energy is supplied or extracted from somewhere. Now notice what has happened to the original question. It's split into two questions, and they're not the same. How can particles come from a state with no particles? How can the whole physical setup, space, time, fields, and laws, come from no physical setup at all? The first question is largely answered within established quantum field theory. No particles isn't no fields, and excitations are created when energy and constraints allow it. The second question is the one people really care about when they use the dramatic phrase, something from nothing. And that second question is much harder because it asks what we mean by nothing when we're not allowed to assume space, time, fields, or even the equations. Before we charge into that, we should pause and face a delicate point that honest physics has to admit. When we say the vacuum fluctuates, we're talking about a vacuum defined inside a framework that already exists, a space-time with a notion of time evolution. fields defined on it, and a mathematical structure whose lowest energy state we call the vacuum. That's not nothing. It's a very specific something with minimum energy. So one may fairly ask, are we explaining creation or merely describing the behavior of an already existing world in its quietest state? And yet the vacuum is strange enough that it tempts you. It behaves like a seething background that can, under constraints, yield real effects. It blurs the line between empty and full. It forces you to abandon the childlike picture of a void as a dead stage. It suggests that what we call nothing is often just the lowest energy arrangement of the ingredients we've decided to include. So here's the real pressure point, the place where curiosity becomes unavoidable. If the vacuum isn't nothing, then what would nothing have to mean for the universe as a whole? And can we even define such a thing without smuggling in the very structure we're trying to explain? To even attempt that, we must notice something peculiar. The moment you say before the universe, you've already invited time into the room. But if time is part of the universe, then before is a questionable word. It may be like asking what's north of the North Pole. That doesn't mean the question is silly. It means the language we inherited from everyday life isn't built for this territory, so we have to proceed the way physics often proceeds, replace the everyday words with operational ones. What could we mean by nothing in a framework where time and space might not be given? In ordinary quantum field theory, fields live on space-time. But in a theory where space-time itself is dynamic, general relativity, space-time isn't a rigid stage. Geometry responds to energy and momentum. That already changes the bookkeeping. In fact, in general relativity, the idea of a globally conserved energy is subtler than in Newtonian mechanics. Energy conservation works locally in a precise mathematical sense. But the total energy of the whole universe isn't a simple number you can always define the same way in every cosmological situation. So when someone objects, you can't get a universe from nothing because energy must be conserved, the honest reply is, conservation laws still exist, but you must be very careful about what total energy even means when space-time itself is part of the system. There's a common intriguing line of thought. Perhaps the total energy of the universe could be zero. Matter and radiation carry positive energy. Gravitational fields, in a certain sense, carry negative potential energy. In Newtonian gravity, you can already see the idea. It takes energy to separate masses to infinity, so bound systems have negative gravitational potential energy. If you add up the positive rest energy of matter and the negative gravitational binding energy, you can imagine a near cancellation. In cosmology, this becomes a tempting bookkeeping picture. A universe with matter and expansion might have a net energy that's zero in an appropriate sense, so creation wouldn't violate an overall energy balance. But this isn't a clean theorem you can write on a postcard. It depends on how you define energy in a curved, evolving space-time. The point isn't that we have a simple conservation bookkeeping proof of creation. The point is that the usual "you can't afford it" objection loses its force once gravity joins the story. Now, how does quantum theory enter? If you treat the geometry itself as a quantum object, you're led to the idea of a wave function of the universe. That phrase sounds extravagant, but it's just the quantum rule applied to the whole system. Instead of a single classical space-time history, you have a quantum amplitude for different geometries and field configurations. In some approaches, the central equation is a constraint, often called the Wheeler-DeWitt equation, that doesn't even contain time in the usual way. Time in that view isn't a fundamental parameter ticking in the background. It's something that emerges approximately when the universe has a classical geometry and certain variables can serve as clocks relative to others. Notice the shift. The question "what happened before" may be replaced by "what does the wave function predict for the geometries that have large probability? And how does a classical time description emerge within them?" This is where proposals about coming from nothing usually live, but we must be strict about what nothing means in these proposals. Typically, it doesn't mean a literal absence of laws, logic, or quantum principles. It means no classical space-time, no pre-existing space and time in which things sit. The nothing is closer to no classical geometry, perhaps a boundary condition on the wave function, corresponding to the absence of a prior space-time region. Historically, two famous kinds of boundary ideas appeared. One is the no-boundary type. Instead of a beginning in time with a sharp edge, the geometry is rounded off in a way that makes the earliest region more like a smooth cap than a temporal cliff. In such a picture, asking what happened before the beginning becomes like asking what lies south of the South Pole. The coordinate that looked like time in later epochs doesn't extend indefinitely. It changes its character near what we call the beginning. Another idea is the tunneling type. In quantum mechanics, systems can transition through classically forbidden regions. The classic example is a particle crossing a barrier it doesn't have enough energy to climb over classically. If you apply that sort of reasoning to cosmology, you can imagine a transition from a state with no classical space-time to a small, closed universe that then expands. The mathematics uses the same kind of amplitude concepts as tunneling, but now the variable is something like the size of the universe. Here's the intellectually playful but crucial check. In ordinary tunneling, you still have time, a particle, and a barrier defined in space. In cosmological tunneling, you're stretching that analogy to a domain where those ingredients are exactly what you're trying to explain. So the analogy may guide calculation, but it cannot be treated as a literal movie of events happening in time before time. If you demand a picture in the everyday sense, little universe bubbles popping into a surrounding emptiness, you've quietly put back the space-time stage you claim to remove. So, where does that leave something from nothing? We can now say something precise and not mystical. If by nothing you mean no particles, then quantum field theory already tells you the vacuum isn't featureless, and excitations can occur when conditions and conservation laws permit. If by nothing you mean no classical spacetime, then certain quantum gravity-motivated models attempt to define a quantum state in which classical spacetime isn't present and from which classical spacetime can emerge as a high-probability configuration. In that sense, something, a classical expanding universe, can arise from nothing, no classical geometry, but only because the nothing still contains a framework, quantum rules, constraints, and a notion of allowed states. And this is the point where intellectual honesty bites. When someone says, then we've explained why there's something rather than nothing, we must ask, have we? Or have we merely pushed the question one level down? Because the moment you accept the quantum framework and its laws, you've accepted a kind of something already: structure, rules, possibilities, and a space of states, even if not an ordinary space. So perhaps the sharpest version of the puzzle isn't how did matter appear, and not even how did space-time appear. It's this: are the laws themselves the kind of thing that can be there without a universe, or is that a category mistake? In other words, when we say nothing, are we trying to subtract the contents of the universe while keeping the rules that describe contents, or are we trying to subtract the rules too? And if we subtract the rules, what does it even mean to ask a physics question? If you insist on the most severe nothing, no space, no time, no fields, no quantum state, no laws, then physics as a method has nothing to grip. Physics explains patterns by assuming patterns. It can tell you what follows from a set of principles with extraordinary precision, but can it answer why there's any principle at all rather than none? So let me end with the uncomfortable question that refuses to go away. When you say nothing, do you mean an empty universe obeying laws? Or do you mean the absence of laws as well? And if you mean the absence of laws, what kind of answer could even count as an explanation? So what have we actually learned if we keep our feet on the ground and refuse to let words do the work for us? First, the everyday nothing isn't the physicist's nothing. When you say an empty box, you mean no stuff I can see or touch. Physics replies, even when there are no particles, there are fields, and even when the fields are in their lowest energy state, they cannot be perfectly still. The vacuum isn't a blank, it's a particular physical state with rules, constraints, and measurable consequences. If you change the conditions, put in plates, accelerate an observer, curve space-time, what counts as empty changes in ways you can calculate and sometimes measure. So one kind of something from nothing isn't creation out of absolute void. It's the appearance of particles and forces from the structure of the vacuum once you ask the right operational question. Second, when you enlarge the problem to the whole universe, the same habit saves you. Define your terms. If nothing means no classical space and time, then it's at least conceivable within certain quantum gravity-style frameworks that a classical space-time could emerge from a quantum description that doesn't presuppose a pre-existing temporal stage. But here the phrase "from nothing" is again a shorthand. You haven't eliminated all structure. You've replaced the familiar stage, classical space-time, with a deeper kind of stage, a quantum state space, constraints, and a rule for amplitudes. It may be a remarkable replacement, and it may be closer to what the universe is really doing, but it's not nothing in the absolute sense people often imagine. Third, and this is the honest conclusion, physics is powerful precisely because it doesn't begin from nothing. It begins from a small set of principles and then insists relentlessly on logical consequences checked against experiment. That method can take you from a few assumptions to the spectrum of hydrogen, the stability of matter, the behavior of the vacuum, and the large-scale evolution of the cosmos. It can show you that empty isn't empty, and that the bookkeeper's ledgers are stranger than common sense suggests. But if you now ask the final question, why there's any framework at all, why there are laws rather than no laws, physics may have reached the edge of what it can properly call an explanation. Not because it has failed, but because the question tries to remove the very platform on which explanations stand. You can subtract particles, you can subtract classical space-time, you can even try to subtract the idea of a fixed background time, but can you subtract consistency? Can you subtract the requirement that predictions be definite enough to compare with experience? If you remove every rule, what remains that could be discussed without contradiction? So how can something come from nothing has a precise scientific answer only after you say which nothing you mean? From the vacuum, yes, in well-defined ways, because the vacuum is a physical state with unavoidable quantum structure. From no classical space-time, perhaps in certain models, but only by invoking deeper rules. From absolute nothing, no entities, no states, no laws, physics doesn't so much give the wrong answer as it loses the meaning of answer. And that leaves a final useful kind of curiosity, one that doesn't pretend we've solved everything. If the vacuum is the simplest physical state we can define, and if even that simplicity is full of structure, then what is simplicity at the deepest level? Are the laws we use truly fundamental, or are they emergent bookkeeping rules from an even simpler requirement, like mathematical consistency, or the possibility of making any predictions at all? If nothing cannot be defined without smuggling in some structure, then maybe the real mystery is what's the minimum structure a world must have so that the very idea of something and nothing becomes meaningful. Think about what we've really discovered here. We started with a simple question that seems almost childlike. Where did everything come from? And we ended up somewhere completely different. We found that the question itself transforms as you look at it more carefully. The naive picture of creation, where you have absolute emptiness and then suddenly things appear, doesn't match what physics tells us is even possible. Instead, we've learned that emptiness isn't what we thought it was. The vacuum, which should be the closest thing to nothing, turns out to be incredibly rich with activity at the quantum level. It's not dead space waiting for things to happen. It's a dynamic entity that follows rules, has structure, and can produce observable effects. This realization should change how we think about existence itself. When we ask why there's something rather than nothing, we're often imagining that nothing is the natural default state, and that existence requires explanation. But what if that's backwards? What if having laws, having structure, having the possibility of states and changes is actually more fundamental than we realize? What if the real puzzle isn't why there's something, but why we ever thought nothing was a coherent option? After all, even our ability to formulate the question, to wonder about it, to discuss it logically, already assumes a framework of logic, language, and reasoning. You can't step outside of all structure and still ask meaningful questions. The history of physics has been a history of discovering that our intuitive pictures are too simple. We thought space was just an empty container, but it turns out to have geometry that bends. We thought time was absolute, but it turns out to be relative. We thought particles were little balls, but they're excitations of fields. We thought the vacuum was empty, but it's a quantum state with energy. Each time we dig deeper, what looked simple and obvious turns out to be rich and strange. So maybe we shouldn't be surprised that nothing itself, when examined closely, turns out not to be nothing after all. Perhaps the lesson is that reality doesn't owe us simplicity at the foundation. It doesn't have to match our everyday intuitions about how things should work. What physics has given us isn't a final answer to where everything came from, but but something arguably more valuable. It's given us a precise understanding of what we can and cannot explain with the tools we have. It's shown us exactly where our current theories work brilliantly and where they start to strain. It's taught us to be suspicious of words like nothing and something when they're used carelessly, and to always ask what those words actually mean in operational terms. And it's demonstrated that even the deepest questions can be sharpened, refined, and turned into something we can actually investigate rather than just speculate about endlessly. That's not a failure of physics. That's physics working exactly as it should, pushing our understanding as far as it can go while being honest about the boundaries.